Hey everybody, it's great to be with you all again. This week we're going to be exploring static electricity, and that is an example of it. We're going to be starting with the basics. We're going to learn how objects gain and lose charge, and we're going to work through some demonstrations, some of which you'll be able to do at home. Let's get started. Have you ever taken your fleece sweater off and felt that static electricity in your hair, that little crackling sound? Maybe you've seen lightning before and heard the thunder after that. Or maybe you've just dragged your feet across the carpet and shocked a doorknob, or maybe even shocked your siblings. Some other examples of static electricity are interacting with your cell phone screen. Your cell phone screen is not pressure sensitive. It is sensitive to the tiny electric charge of your fingertips. Additionally, taking clothes out of the dryer is a great example of static electricity. Maybe you've opened it up before and tried grabbing some clothes and you felt the shock on your hand. Those are all great examples of static electricity. To understand static electricity, we need to understand the basic structure of an atom. And if you recall from chemistry, we have three basic atomic particles. The first being the proton, which is in the nucleus. The next being the neutron, which is also in the nucleus. And then there's the really tiny electrons that orbit the outside of the nuclei. And a basic fundamental property of static electricity is the idea of charge, where opposite charges attract, where the proton is the positive charge and the electron is the negative charge. Okay? And if they have opposite charges, they will exert a force on each other to attract. And on the other hand, we have like charges, they must repel. And let's say we have two protons that are next to each other. They are both positive charges. And if they come close to one another, they will exert a force on each other to accelerate apart. And similarly, if we have two electrons, two negative charges, they must also repel. And a good way to demonstrate this is this tape demonstration that I have right here. All right, so here's a demonstration that you could do at home. All you need is some Scotch tape. First, take a couple pieces of Scotch tape, lay them down on the table like this. Then just lift them right up. Okay. And all you got to do is bring them together. You see how when I bring them together that they start to repel each other? Well, what happened here was the adhesive on the tape pulled electrons from the table, and now both these pieces of tape are negatively charged, so they repel each other. Like charges repel. All right, so for the next part, you need two more pieces of tape. I have one laid down on the table already. Now I'm going to take another piece of tape and lay it right directly down on top of that. Okay. Then you lift them both up and separate them. Now, when I bring them close to each other, they attract each other. Basically what happened was the bottom piece pulled electrons from the table, and then the top piece pulled more electrons from that one, making the bottom one more positively charged and the top one more negatively charged. So opposite charges, they attract. You might have noticed during that demonstration that I mentioned electrons that were being taken from the table and put onto the tape, and taken from one piece of tape and put onto the other piece of tape. Why is that? Well, earlier we just talked about the structure of the atom and how the protons and the neutrons, they're in the nucleus. They're very large, massive particles compared to the electron. The electrons are very, very tiny and they're orbiting the outside. Well, the protons, since they're so big, they are locked in the center of the atom. Where the electrons, they're on the outside, they're orbiting, okay? Most of them are locked in where they're at, but the ones on the very outside, in the outer shells, we call those free electrons. And through that idea, we can view static electricity as the movement of electrons. So if an object or an atom has excess electrons, it is more negative. And if it has lost some electrons, we call it positive. Now let's look at the example from the beginning of the video. For those of you that don't know, this is my trusty lab assistant, Carl. He's almost 1 year old. on the 11th. But for the example, the balloon has a net overall neutral charge. That means it has the same number of protons as it does electrons. And the same goes for Carl. Same number of protons as electrons. Well, when we took the balloon and rubbed it on Carl's fur, well, Carl's fur gave away a bunch of electrons to the balloon, which gave the balloon a net overall negative charge. Well, if the balloon has a net overall negative charge, why does it want to stick to the wall? Well, let's look at the wall. The wall is also neutral, same number of positive charges as it does negative charges. Well, we know that the protons are positive and they can't move because they're very large. But what actually happens here is the electrons in the wall, they move. So the protons, they stay, as you can see right here, but the electrons, they don't want to be by the electrons in the balloon. So the electrons actually get pushed as far away as they can in those atoms, okay? Which leaves the positive charges closer to the balloon. And since opposite charges attract, they want to stick together. All right, now let's look at material properties for conductors as well as insulators. All right, so that's an example of polarization. The balloon has a net overall negative charge, which polarized the atoms in the drywall. And the way it could do that is because this balloon is an insulator, and so is the wall. Since they're both insulators, that means the charges cannot flow on or through the objects very easily. On the other hand, we have a copper wire right here. Yes, on the outside it's got an insulator, but on the inside it's a copper wire, which means it is a great conductor. Charges can flow through the wire very, very easily. Okay? And it's able to do that because it has more free electrons than insulators do. Okay? With more free electrons, the atoms inside the wire, inside the conductor, can gain electrons from the atoms next to it and then release them to the atoms that are on the other side. So we can pass charges fairly easily. Okay. So some other examples of insulators, I've got a PVC pipe right here, which is just plastic, a styrofoam cup, and I guess I just have the latex balloon. Those are great examples of insulators. On the other hand over here, I've got a pie pan, a soda can, and this metal slinky right here. I don't know why I have this, but it's metal, it's a conductor, and charges can flow on it fairly easily. All right, so that's all. We're gonna use all these examples in future videos. So I don't just, have all this stuff and, play around with trash all day. So, all right, see ya.